For the introduction. Hello everybody, my name is Lukas and I'm happy to present our paper here. Don't think I need to repeat it another time. So I'm part of a team of researchers from RWTH Aachen University. So we focus on industrial construction use cases, so robotics in pre-production and manufacturing, as well as on-site construction automation. For this, we have in Aachen something called the reference construction site. You can see it on the right. So it's a full-scale construction site for research, where we can test our developments in full scale and in a real environment. And my personal focus here is on linked data-based digital twin systems for construction sites that I test here. So if you move your research from the lab to the construction site, one of the first things you realize is that you have a problem with your network and how you network your data. So you observe that a stable and performant wireless network is crucial for construction automation. So cable-based networking is just not suitable because nearly all machinery is mobile and needs to move. And it's really important also to think from a perspective of onboard processing powers of the machine. So not all machines on a construction site, even if we automate it, are super capable robots. There are also some super basic machines like construction lifts, and you probably won't put so much processing power in them, so you need to connect them and network. A second observation is that the reliability and the performance of data transmission in radio networks, so the mobile networks, are affected by building elements and their material composition. So unlike in industrial environments, all finished building wireless networks in construction sites need to cope with a dynamic, changing environment by design. So the construction site is there to progress. That's its job. We have some available indicators for the radio frequency network quality. These are the reference signal strength indicator, RSSI, and reference signal received power, RSRP. Here you can see one of our mobile robots. So our research spans to do construction logistics with it, exploring machine-to-machine communication, for example, for it to use a construction lift on its own, and enhancing its sensing capabilities on the site. All of these use cases need a reliable and performant network connection at all times. So it would be really helpful if we could know beforehand how the network behaves with the construction progress, so we could act accordingly. So on the one hand, we could use the capabilities of nomadic network infrastructure. So we can adapt the network physically, for example, by tilting the antennas in another direction, and digitally, it's so-called beamforming. On the other hand, having a predicted RSSI value, we could alter the navigation of our robots, for example, to make sure that they use a path where we expect the network to be suitable. For this, we need to simulate and predict the network performance. As we already use a linked database digital twin of the construction site, we already have building data linked with schedules, processes, and the relevant machine resources, machine interfaces. So we know when to expect a new building element to be erected. However, what is missing is the relevant data we need for signal strength estimation in our system. So our approach is to include and link data that is relevant for wireless network prediction to existing linked building data and digital process twin approaches for construction sites. So let me quickly give you an overview over the scientific research area. So radio frequency networks planning normally is performed for consumer cellular networks, like your phone network, and it's done on region or city scale. Some software can include rough geometry, for example from OSM or CTGML, or some BIM integration is also there, but it's not detailed building models nor construction sites, and it does not map building progress in there. We also have limited possibilities to include building materials, so if possible, most frameworks support something as material for the whole building, so the whole building is brick then. So there's data about material properties that is relevant to the wave propagation, but this data is rare. It's often created in lab environments and in separated setups. It's just not reflecting real-world construction context. Also, research about radio frequency wave propagation in construction consists of many empirical studies. They oftentimes share the problem that their results cannot be easily generalized because they use super specific setups to test this. So to understand what data we need for signal strength estimation, we have to quickly look at the radio wave propagation basics. So radio waves are electromagnetic waves and can be described using basic wave propagation concepts. The information we want to calculate is the power ratio at the receiver side. This is dependent on antenna properties like power and gain of the transmitter and the properties of the receiver. Moreover, a big factor to be calculated are the losses that are influenced by the built environment, for example, and the topology. According to the ITU recommendation P2040, we use a simplified model for these total losses. Here we mainly distinguish between the free space loss, loss by reflection, and the attenuation loss when the waves penetrate the building and its materials. So free space loss can be calculated when the site and building geometry is known and the position of the transmitter and receiver. For reflection and attenuation, geometry and materials are relevant. Among the necessary material properties we need is the material's behavior as dielectric or conducting. As we have the needed values for a collection of materials in the P2040 recommendation, we at least have all necessary data we need to calculate the attenuation. Therefore, we first focus on this. That we can use this data in our system, we need to have this in our linked building data. If not already known, linked building data is linked data principles applied to AEC. So here we use graphs consisting of triples written in RDF, structured by ontologies. While we already have ontologies for many use cases here at hand, we don't have one that enables to map the data that I just described. To change this, we developed the construction network ontology, CNO, according to the Ontology 101 method. We use 5 simple competency questions to create simple concepts. Our goal here is to extend existing ontologies to enable this. We have 3 main classes. So we have the CNO antenna class, which can be specified as transmitter or receiver with all its properties. We have the CNO obstacle class, which can be a building element, for example, and then linked to a construction process. And we have the CNO material, which can be a conductor or dielectric with properties aligned to the ITU 2040 recommendation. So here you can see our setup on our site. So we run a 5G construction site network. We have an alpha wireless antenna on one of the cranes, a MySite 5G router carried by an INOC mobile platform, that's the robot I just introduced, and a scheduled wall. Here's a duplex brick on block 6 material layer wall. As an example, here's how we modeled our antenna. It is of class CNO transmitter, has modeled data like frequency, power and gain, as well as position and directionality. For the elements, we mapped the class CNO obstacle to the building elements, and we use the material structure in the IFC OVL. Here we align IFC material with the CNO material class and put in all the needed values. To enrich the model, we used a simple JSON with the needed coefficients. We used a vector store and a similarity search to find possible matches, as the material names in the IFC models normally don't match with the one that we have in the standards. Coming to the proof of concept, the free space loss can easily be calculated by grabbing frequency and the position of transmitter and receiver. As we want to be able to predict the network according to the building process, we reuse the process concepts of schedule and status from the IOC process ontology. These define the point in time when we expect the building element to be realized. Getting the planned elements by the schedule information, we query for the relevant material properties. This query is a little bit more complex because of the IFC old structure. The calculation here shows the results in attenuation per meter for one material. So we do this for all layers and multiply with the respecting layer thicknesses. Filling in all results, we can calculate and predict an expected RSSI value at a specific point for a specific scheduled building progress. To conclude, we developed a simple ontology to extend LBD data models with data that describes the basic of wireless radio frequency network infrastructure. We enabled interoperability between domains by linking data from construction, scheduling, LBD, and radio frequency network engineering. And we exemplarily queried our triple store for data to calculate a reasonable RSSI value as proof of concept. Our study is, however, also limited, so ontology and proof of concept calculation is limited to simple accessible values. So right now no reflection, refraction, and scattering is included, as values for the albedo roughness and refractive index are required for this. This is probably the biggest limitation right now. The availability of these values in official material is just highly limited. So we published the ontology draft according to best practices. And to finish this presentation, I want to give you a small outlook. So as we now showed that we can include the needed data for basic signal strength estimation in our link building data, in the next step, we want to extend this to more data to calculate also the reflections and the scattering. And then we want to focus on automating the simulation workflow. This is already in work. We follow here a ray tracing based approach. To make use of the expected information, we need to solve how to hand this over to the control mechanisms for the network equipment, for example, for tilting and beamforming. And in addition, we want to explore how we can use this information best in our existing ROS-based navigation solutions for the mobile robots to use it on site. And with this, I thank you for your attention.